All right, so like I said, it's just, we remember what the words for product and product and quotient are. We're looking at functions that have multiplication and functions that have division. So what is our rule if we have a function that is two functions being multiplied together? So if we see something like this, we're asked to take the derivative of function u times function v. Well, the product rule says this: take u, unchanged, the function u, times the derivative of v, plus v times the derivative of u. Or in words, as we look at that, we could say the first times the derivative of the second, plus the second times the derivative of the first. This is a product rule of two functions. The nice thing about product rule or multiplication and this rule is that it's all multiplication and addition. Order doesn't matter. So if you were to get it flipped around backwards, it actually would give you the exact same answer. The other thing is that this is expandable to more than just two functions. If you can kind of just follow the pattern, we can multiply as many as we want to. And all that's really happening is you're just taking turns working through the product, taking turns taking the derivative of each different one. So let me give you an example of something more than two functions being multiplied together. If we were to look at something like the function a times b times c times d, where a, b, c, and d are each their own individual functions. Taking the derivative of that, I basically can just go down the line and take the derivative of, take turns taking the derivatives of a, b, c, and d while the others don't change. So a, b, and c could stay the same times the derivative of d, plus maybe the second time we take the derivative of c. And then we take the derivative of b. And then we take the derivative of a, where we just alternated until we've gone through and taken the derivative of each one of those down the line. Okay? Questions on that? All right. So let's look at an example of what product rule would look like. Our function up there is two binomials multiplied together. Well, that is product rule. That is two things being multiplied together. We can apply our product rule. And our product rule says we take the first times the derivative of the second plus the second times the derivative of the first. One of the things we want to make sure that we are getting used to is labeling what's going on. So up here it says take the derivative of this. And notice down here I'm saying our derivative equals, and then I'm going to put our answer here. So our formula says take the first, which is x squared plus 3, times the derivative of the second. Well, the second is just a polynomial. I can apply my power rule. Its derivative would be 3x, subtract 1 from the exponent, squared, and the derivative of 5 would be 0, plus our second function, which is x cubed minus 5, times the derivative of the first. And again, the first is just a polynomial that I can apply my power rule to, and I would get 2x. As always, in a free response format, we could totally stop there. Typically, we are using this for something where we would want to clean that up a bit. So ways that I would clean that up would be distribute on both of those and combine my like terms. If I were to distribute, let's see, we would get 3x to the fourth plus 9x squared, 2x to the fourth minus 10x, which would give us 6x to the fourth plus 9x squared minus 10x, just an equivalent form of the same answer. Any questions on product rule? Yes. Thanks. Okay. Quotient rule. Quotient rule means we are dividing, and this one is a little more complex, and order matters on this one. So we are taking the derivative of some function divided by another function, u divided by v. Our derivative format for quotient rule says this. the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, and all of that will be divided by the bottom function squared. Because we're now switching to subtraction, order does matter on this one. You have to do the bottom function times the derivative of the top first. This right here in parentheses is kind of a little phrase or whatever rhyming phrase that can kind of help you remember the order that it goes. And it says low D high. Low D high refers to this. The bottom function times the derivative of the top. Low times the derivative D high, derivative of the high function. Low D high minus high D low over low squared. Okay, so if you like that, if you like just saying it out in more words, bottom function times the derivative of the top plus top function times the derivative of the bottom. However you need to remember that, you got to remember the order that that goes. Okay. So let's go ahead and try one here. It says differentiate f of x equals x squared minus 1 over x squared plus 1. So following our format here, again, always labeling what I'm doing. So right now I'm taking the derivative of f, df dx, and it's a quotient rule, so it's the bottom function. And I'm going to go ahead and color code this so we can follow what we're doing here. We'll do our top function in green here. Bottom function times the derivative of the top. Well, the top function's derivative would be 2x minus the top function times the derivative of the bottom, which again, we can just apply our power rule and get 2x all over the bottom function squared. Again, stop there if you don't have anything else to do with this so we don't make a mistake. Typically, we have to go on, so just helping us clean this up algebraically. Remember, I would distribute both the 2x and the subtraction there to be able to combine my like terms. So we would get, let's see, 2x cubed plus 2x. Distribute the negative, distribute the 2x minus 2x cubed minus a negative, so plus 2x. Usually where you are going with this, you will not need to FOIL the bottom. However, sometimes you do. I would not suggest doing it early unless you find out that you have to by the end. So this one would finally clean up to 2x cubed minus 2x cubed would be gone. 4x over x squared plus 1, quantity squared. Any questions on quotient rule? All right. So go ahead and take a second and practice that quotient rule without me doing this. Given the function y equals 3x to the fourth minus 5x squared over x cubed, it says find y prime. So take the derivative of that. I do have up there method 1 and method 2. Method 1, I want you to just practice what we just did. Do the quotient rule, and then we're going to talk about some options that we have sometimes depending on what the function looks like. But this one, I just want you to practice, first of all, your quotient rule. Try to clean this one up as much as possible algebraically. There's a bunch of different ways that you can, or places you could stop at the end of this one, but I want you to see if you can clean it up as much as possible. Okay, let's try our quotient rule. Quotient rule says low D high, bottom times the derivative of the top, which would be 12x to the third minus 10x, minus high D low, 3x to the fourth minus 5x squared times the derivative of the bottom, 3x squared, all over the bottom squared. How are we doing with the setup so far? Good? Low D high minus high D low over low squared. All right, cleaning this up, I would distribute both of those, including the negative here. So let's see, we would get 12x to the 6th minus 10x to the 4th minus 9x to the 6th plus 15x to the 4th over x to the 6th. Combine my like terms. 3x to the 6th plus 5x to the 4th over x to the 6th. Now, if you got to this point, you're doing great, but I would say that this is not done because you have a common factor in the top that you can factor out and simplify with what's in the bottom, right? We have a GCF of x to the 4th in the top. And that x to the 4th can simplify with the x to the 6th in the bottom. So they would get 3x squared plus 5 over x squared. And I'm going to pause there. How are we doing? All good with the algebra? And I'm going to take this one step further. Because you have a common denominator of x squared, we could write each of those terms over x squared. Well, 3x squared over x squared, your x squareds would cancel, and you would just be left with 3. And then 5 over x squared would not simplify. It would just stay 5 over x squared. So we could go all the way down to something like 3 plus 5 over x squared. Doing okay with that algebra? Okay. All right, now I told you that there was a second method on this one. The second method is this, and this only works on a quotient rule where we've got a monomial in the bottom, is that I really could have done that simplifying that we did right here, where we broke it over the common denominator. We really could do that up here, couldn't we? Is rewrite each of those terms over the x cubed. So I'm not taking the derivative yet, but I'm going to simplify. And then I'm going to just follow my power rule once I get it written more as a polynomial instead of as a quotient. So if I were to put each of those over x cubed, 3x to the 4th over x cubed minus 5x squared over x cubed, we can see that our function would simplify down to, but my x's would cross off there. I'd be left with 3x and 5 over x. I'm going to take this one step further before I actually do the derivative because we saw this hidden power rule on Thursday, and we said it's probably easier if I write it as x to the -1 as I'm doing my power rule, right? Anytime that x is in the bottom, probably just easier to slide it up to the top and give it a negative exponent. Now, as I do my derivative, it's just my power rule. Well, right here, 1 times 3 is 3. Subtract 1, that x is gone. -1 times -5 is a positive 5. Subtract 1, it'd be x to the -2, and that -2 we could drop back into the denominator. A lot less work, right? So, awesome if we can avoid our quotient rule. Can we always avoid our quotient rule? No, that was not an option. If we flip back to this, that's not an option here, is it? Because you've got a binomial in the bottom. It's not going to fix anything by separating it both over x squared plus 1. Okay, so great. Look for the monomials in the bottom and avoid your quotient rule if you can, but you got to know your quotient rule. Okay, we're going to do that same thing here. We're going to look at two methods here. First one, we're looking at product rule, right? Very similar to the one we did at the beginning. I want you to try this one using product rule, see if you remember the order. And then we'll talk about a second option and when we can do that. Okay, the whole idea behind the product rule is we're just taking turns taking the derivative. Keep the function the same for one of them, take the derivative of the other. It's all addition, so order doesn't really matter. What we saw was first times the derivative of the second, so our first is x cubed plus 2x, times the derivative of the second. Well, the derivative of x squared minus 1 would be 2x, plus the second function times the derivative of the first. So power rule again on that first one, 3x squared plus 2. Good so far? Probably would need to clean that up because usually it's not just a question of take the derivative of this function. We're usually using it for something. So let's look at the cleanup process here. Distribute right here, we would get 2x to the fourth plus 4x squared. FOIL over here, 3x to the fourth plus 2x squared minus 3x squared minus 2, and combine like terms. All right, we have 2x to the fourth and 3x to the fourth, which would be 5x to the fourth. 4x squared plus 2x squared minus 3x squared would be 3x squared minus 2. Done. Now, I said there was a second method. Any guesses now looking at what we did last time, what that second method might be? FOIL it out first. Absolutely. If we are looking at two polynomials, you absolutely can FOIL first, and then it is just a power rule problem. So again, without changing anything, all I'm doing is FOILing first. I am not actually taking the derivative right now. So if I were to start by FOILing that, let's see, we would get an x to the fifth minus x cubed plus 2x cubed minus 2x, which is x to the fifth plus x cubed minus 2x. And then we just apply our power rule. 5x to the fourth plus 3x squared minus 2. And you can see we got the exact same answer. Now, could we have done that on the first example we did with product rule? If you go back and look, it's also just a binomial times a binomial. So when can we, or when would we not be able to? Why wouldn't we just always do that? Doesn't that seem a lot easier, right? FOIL it first and do our power rule. We just aren't quite to this yet, but it doesn't always work. Why not always simplify first? It's not always an option. We're eventually going to get to something like where our function is x times the natural log of x. We don't right now know what the derivative of natural log of x is. We will. But there's nothing to do to simplify this. You have to use your product rule on something like this eventually. Once we've learned what natural log of x's derivative is, we can do that. Okay, so that's why we have to learn these, is that we saw one where quotient rule we can't simplify. This one you can't simplify. You got to know your rules outside of that. All right, last one we're going to look at is this. One of the super common things that we will see a lot in calculus is talking generically in variables, referring to functions as variables. So we've got some function u and some function v. They tell us that the value of the function u at 2 is 3 and its derivative at 2 is negative 4. that the value of v at 2 is 1 and its derivative at 2 is 2. And we're supposed to then figure out what the derivative of u times v is at 2. Okay, well, what we're going to do is just use our power rule or our product rule, because we're looking at a product, to find what that would be in terms of variables and then just plug in our values. Okay, well, this is, if I get rid of the 2, that's just our definition from earlier, right? So it's kind of easy to follow that one. Doing our power rule here says that you would take the first times the derivative of the second plus the second times the derivative of the first. And all I need to now do is go up to the information given to us at the top and replace each of those with their value at 2. So u, which would be this one's, value at 2 is 3. The derivative of v at 2 is 2. V of 2 is 1. And the derivative of u at 2 is negative 4. So then I just replace each of those with their correct value, simplify, and we get an overall answer of 2. Okay. Questions on that? Okay, so let's look at the second one. D dx of 4u plus 3v. Can we talk about that 4u part of it? Is that a product rule to do this? Will I need product rule to do the derivative of 4u? What do you think? Is it multiplication? Do I need to do the product rule? We talked about scalar multiples in derivatives, didn't we? We had a rule that said that if we've got a function being multiplied by a number, we can just take the derivative of the function and just multiply the result by that number. That was one of our rules we've talked about. What if I forgot that? Would I get the wrong answer if I did the product rule? You wouldn't. I can follow my steps for the product rule that says take the first times the derivative of the second plus the second times the derivative of the first. Well, what's the derivative of 4? 0. Well, wouldn't this just be 0? Okay, so you're going to see that we would still end up just taking 4 times the derivative of u because this would be 0. So it's not wrong to do the product rule. It's just a lot of extra work that you don't need because the derivative of a constant is always 0. So all we need to do is 4 times the derivative of u and 3 times the derivative of v. And again, we're replacing then derivative of u and derivative of v with their value at 2. So derivative of u at 2 is negative 4. Derivative of v at 2 is 2. And we get negative 10. Questions? All right. Your assignment is on page 124. You're doing 13, 14, and then 16 through 24.